Log on, tune in, find out. Another good idea from Cambridge.
Of the afternoon, Prasad Tetali will tell us about transportation and related inequalities in discrete spaces.
Thank you. Thanks to the organizers for inviting me. And I don't see the other Prasad here, which makes me worried. At some point, I started wondering whether they meant to invite the other Prasad and did me by accident. And to be safe, they invited both of us. But it's a pleasure to be here. And up front, let me say there's not going to be any Fourier analysis in this talk, or harmonic analysis. It is discrete functional analysis. So in case you were hoping for more Fourier analysis since Ryan's talk, the advisor, organizer kindly tried to warn you. And also, I won't assume that you were here in my talk a few years ago. I did talk about this topic, so I'll remind you about what it was about. And so, unlike Ryan's talk, I will mention several inequalities. I will spend some amount of time on the first inequality, but I won't go nearly as much into the depth as Ryan did in terms of giving proofs. And I'll mention my motivation in studying some of the inequalities and mention connections between them. Some of this is inspired by what people have been doing much more intensely and with much more success in continuous spaces on Rn or other spaces. And in discrete spaces, because of the lack of usual calculus, things are much more difficult sometimes, some of them. And so in some ways what I'm able to present lags quite a bit behind compared to the results in continuous spaces. And in particular, later on in the week, you'll see a talk by Dipra and also Sturm, who will talk more about the continuous spaces. And the results there would be much more impressive. Okay, so I'll say what I mean by the sub-Gaussian constant, and then I'll go to a different interpretation of the same inequality that defines the sub-Gaussian constant using the so-called transportation problem. And then I'll mention connections to variants of logarithmic Sobolev inequalities, how these are related. And I'll conclude with, depending on the time, with some very recent work with a few people at Montlhévelay in Paris, who inspired me to come back to this topic that I had sort of left a few years ago after graduating one of my students who was working on this. Okay, so to start formally, for the most part, I'm going to assume by a discrete space finite graph, or some of the time a random walk on such a finite graph. And I'll have a probability measure on the graph, or a measure that the Markov chain or the random walk converges to. And much of the time, you could think of that measure as being uniform on the state space. So if it's a graph, it's going to be uniform. You could think of it as just uniform on the set of vertices. And if you have a Markov kernel, you could think of the invariant distribution being uniform. Okay? But there are some interesting examples where it's not necessarily uniform. And the class of functions over which I'm looking at a bound on the moment generating function, expectation of e to the tf, the class of the set of functions that f belongs to is what I'm going to describe as being Lipschitz. So on the graph, by Lipschitz, if you have the usual graph distance, namely the distance between a pair of points is the length of the shortest path between the pair of points, and let's say nearest neighbors have length 1. So for each edge you have weight 1, and this is the simplest. And so for not necessarily neighboring points, it's the length of the minimum number of edges in a shorter span. So by Lipschitz, then it amounts to saying across an edge the function differ by at most 1. Okay, if you have some other distance on the same graph, you could think of it as the usual 1 Lipschitz. Okay, so the Lipschitz constant is 1 for me throughout. Over that class of functions, I'm trying to bound the moment generating function. Okay, these functions defined on the graph. So I have 2 parameters besides the graph and the measure pi, and the 2 parameters are t and f. And I would like a uniform bound. On the right hand side, that's a sub-Gaussian bound. Okay, sub-Gaussian because sigma of g could be some quantity that depends on g and pi. And just to simplify notation, I'm going to drop pi much of the time because pi, the probability measure on the space, is uniform over the finite set. So I'll typically represent it as sigma of g, although it should depend on g, d, pi, and also. Okay.
And the fact that you're working on the graph is only entering the Lipschitz condition.
Yes, exactly. Okay, and so that's the. Okay, so why, you might ask, or bounding moment generating functions is a fairly natural thing to do, but just to be sure, so using a standard argument, referred to as Chebyshev argument, you can derive from that a deviation inequality in terms of how much the function changes, say from the mean. Right, so you get something like equation 2, where the constant on the right hand side depends on our sub-Gaussian constant. And sometimes, as you'll see in the next slide, you might want deviation from a median rather than the mean. So my m of f is a median with respect to the underlying measure, okay, with respect to pi. And usually you try to show that the mean, if you're looking for any sort of concentration or deviation, you hope that the mean and median are not too different, and so you use some inequality then to go from 2 to 3, where typically you lose a little bit, you lose something. And so just bounding, question?
In 3 somehow don't you want to bound from above that f is
Yes, sorry, this is a typo I didn't fix. This is greater than or equal to h.
yeah, so actually
I fixed that, yes. I thought I fixed the inequality. I fixed the wrong inequality. Sorry about that. So again, this should have been, so these 2 inequalities should be just like above. Right? Okay, so the deviation from, if I had done 1 minus, I could have been. Okay, that's good. So everybody knows what I'm talking about. So again, f minus mf bigger than h, right? You're away from median by some h, is small. So sorry about that. This should be swapped, the inequalities.
What is C sub var?
Right. So the point is, because I did some fudging to relate the mean and the median in terms of variance, I want some global bound on this variance over all functions, and that I'm going to denote as C sub var of g, although it should again depend on g and pi, and that's simply, it's a different constant, in a sense conceptually much easier one to think about, rather than bounding the moment generating function over the class of Lipschitz function. How about just bounding the variance? Okay, so now again you are given g, pi, and then now you're just bounding over the set of Lipschitz on the graph variance. Okay. And this was actually studied before us in a nice article by Nagalwan, Ravi Bappana, and Joel Spencer, and they called this the spread constant. So C var I'm going to refer to as the spread constant, as opposed to sigma, which is the sub-Gaussian constant. So I'll come back to the spread constant a bit more. As I said, you might want deviation from a median. Again, this is all classical, so I'm probably offending many people by trying to say these what should be classical and more or less routine. So typically, one of the reasons you might want to study a deviation from a median is because you're interested in some isoperimetric inequality. You have some, like the one initiated by Harper. So you take some subset A, denoted here, of measure at least a half, let's say, and then you want to say most of the space is within a short distance of your set A. In other words, if you take an enlargement of size h, namely all the points that are within h, then what's outside, so in my notation pi of x such that dxa at least h, so all the points that are outside a ball of radius h amount to very little. Right? So they're exponentially small. You want to say it's e to the minus h square over 2 up to some constant, where the constant of course depends on the space g, and so if the median plays in because if you take pi of a at least 1/2, then you can capture the fact that f of x has such a function has median 0 using either this set or complement. Okay, so that's so this is one motivation, the item 1. We had so our beginning was actually inspired by a question of Talleyrand on product spaces. So his question was, can you somehow not lose in the exponent h minus something or h square? Can you get more or less optimal type of h square over n because you're on an n-dimensional space by paying some cost in front? Okay, is there some constant, absolute constant k, so that you can get an inequality of this type, where so his question was about general arbitrary product space, product measure, but the distance is a Hamming distance, so as long as they differ in some coordinate. Okay, that's one. And he did much of the work, actually. He did much of the work in the sense that over several pages of several lemmas, he reduces the problem to solving this question just for the discrete cube, general p1 minus p product measure on the discrete cube, but for just the down sets, so sets closed from below.
So A superscript h is the set described above.
Yes, so A superscript, it's a complement of what's described above.
Okay.
So 1 minus this,
Yeah, okay.
A to the h is the enlargement of size h, meaning all points that are within distance h from some point in A.
And n, it appears in the denominator of the exponent. So
Yes.
this
what's happening?
sigma of g is n for the example that you're thinking of.
So let me go to this slide. So both the subgaussian and the spread constant, like any respectable functional inequality you try to work with, tensorizes. In other words, for our graph setting, there are many product graphs, but if you take the notion of the product graph, that's a so-called Cartesian product, that gives you, when you start with an edge and take n-fold product, that gives you the discrete n cube, and you start with a cycle and take the n-fold product, discrete torus, and so on. For that product, when you have a product measure, it's easy to show that these tensorize in the sense that the quantity on g to the n is captured by what's happening on g. Because of normalization or whatever reason, here there's a factor of n. In continuous spaces, typically, you have dimension-free inequality, meaning it doesn't depend on n. Here, by the nature of it does, but at least the complexity is in understanding what it is on g. So going back, and this is the motivation. Of course, it would be not so interesting or kind of easy if I'm trying to understand concentration or deviation on any, on little graph, such as the cycle or whatever little graph. But the point is, if you're able to bound the subgaussian or spread constant on the little graph, because you can take the same value and you understand it on g to the n, now you play the rest of the game on g to the n. And so that's how you get an n. So what I had before was sigma square of g, and we'll go to the discrete cube case where sigma square n sorry, in our paper we call it sigma square. Here I dropped the square. It's just sigma. Both the sub-Gaussian and spread constant for, say, if you take the uniform measure on 2 point, would be 1/4. I mean, variance is clear, it's 1/4, and it turns out also the sub-Gaussian for that case. And so when you go to the n cube, it would be n times 1/4. And so if you have something like h squared over 2 times n4, that translates to 2. Yeah.
So on expanders, we expect this to be an absolute constant?
You jumped ahead. So this was the point. This was sort of towards the end of my lecture when I last spoke on this, when Svante Janssen asked me, you're talking about all this, the sub-Gaussian and the spread constant. Can you give me a family, can you give an example where these are substantially different? Or are you wasting our time? Most of the time the variance tells you everything. And we had, somehow not such a compelling example, like the weighted 2-point space and so on. But I think, one of these quick reactions should be taught to everyone, that to say, how about bounded degree expanders? So I'll show the example that shows that on that class, these are actually different. So the spread constant, as you said, will be bounded, but the sub-Gaussian is not. Yeah. Unfortunately, I didn't have that answer last time. Okay, so just to mention, this kind of inspired us to take a general look at general graphs and so on, this concrete question, saying, okay, can we understand what's the exact value or as close to it as we can in a general setting, the question of tau, besides settling it. So it turns out solving this was, it took just the first 2 pages of our paper or something. There were some classical results of Jogdev and Samuels we could use that relate the mean and the median of a binomial distribution in terms of if one is an integer, what can you say about the other one, how close to it, and so on. And the result of Bolabash and Leader on Cartesian product spaces. So using some known results and some work, we could settle Talleyrand's question in the affirmative.
For the variance one, is it the same constant as in the Poincaré inequality?
Again, no. Yeah. So all this I'll get. I'm glad. So at least one person is interested in what I'm saying. Yeah. So, but not to leave you hanging. So in the Poincaré inequality, you have say the Dirichlet form or something divided by the variance, and so you can bound it, but the bound is not going to be tight in general. Yeah. It gets you a bound. Yeah. Because you have Lipschitz functions, you can bound the numerator. Yes. Okay, so just to again make sure that the second moment, of course, it should not be surprising. Is it's going to be, or the sub-Gaussian is going to be smaller than the second moment, and just formally you can do it by the Taylor series expansion. So let me mention as to why Alon, Bapana, and Spencer studied this question. So they looked at g to the n, so Cartesian product. Again, if you're not familiar with the Cartesian product, you have some underlying graph g, and then on g to the n, you have an adjacency. So x1 through xn is adjacent to y1 through yn if all of the xi's are equal to yi's except in one coordinate. And in that coordinate, you should be adjacent in g. Okay. So for the discrete cube, it's just changing some 0 to 1 in some coordinate gives you adjacency. But another interesting graph is a more general Hamming graph. You could start with a complete graph and take the product, and that's another interesting example. So in such a product, what they were interested in is the following question. Now you take an L1 type distance. So you have the underlying graph where there's some graph distance, and the distance on g to the n is just sum of the distances. Okay, by that's what I mean by the L1 type distance. and the third is the measure. So the measure is just a product. Okay, let's say again, say uniform or something. In such a setting, one of the results they showed, which is quite nice, is that if you're interested in sort of medium to large deviations, okay, so notice that we're on g to the n. So if you think of the distance in g as being some large constant, then in g to the n it's at most some constant times n. So it's never more than n times the whatever diameter in g. And so here we're looking at deviations that grow larger than square root n but are little o of n. In that range, they were able to pinpoint exactly what happens in the exponent. Okay, this is actually what they showed. I think the title of the paper is an asymptotic isoperimetric inequality. They showed actually that this is the right bound also from below. So what is this? This meaning, so my h square over 2 times. So typically we had sub-Gaussian here. In this case, for this range, they showed that in fact just the second moment tells you what you need to know. So this was their motivation to give it a name and study this so-called spread constant.
When you say it's true from below, there exists some A which shows that it's right from below, or this is what happens for every A? No, it must be there exists some.
Yeah, I think, but there's a sequence. I think there's a sequence. Is that right? Let's see. Yeah, I don't remember, unfortunately.
No, yeah, okay.
Actually, I think maybe for every A, so I want to bound 1 minus. So right now I wrote an upper bound.
This
right?
says that,
but
it expands very, very quickly.
Right.
Right.
Yes, but every A with measure at maybe I have it. Measure at least 1/2.
But there are A's for which it does expand much faster than this.
Right. Right. And if below this you may not be so interested in it, but for very large enlargements, very large deviations, they showed that it's more complicated. It's not simply the second moment. They defined some 2-player game. The players named Lipschitz and Bernstein or something, and they show that the value to this 2-player game is actually the answer that tells you what. Yeah, that's okay. So I talked about tensoring. All right. So here are some examples that we computed. This is just to show that some of these quantities are actually quite difficult for us to estimate. So there are very few examples where I know the precise values. Okay, so of course the 2-point space is always the place to start for many of these things. If that's difficult, then that means you're in the wrong problem or wrong field. And then the asymmetric case, when you have P1 minus P, curiously takes the form of something you might have seen. I think that's the inverse, or it is, depending on which side of the log sub 11 inequality you put the constant. It comes up. It takes this form.
P equal to a half. You're saying?
Yeah. So you have to take the limit and show that it actually.
Oh.
Yeah. So this is for P not equal to half. So this is for P not equal to Q, obviously. And so that's the case where again the two differ, the weighted 2-point space. But this is still somewhat of a puzzle. We don't know, besides computation giving the same value, we don't know why this actually coincides with something that comes up in log sub 11. in terms of general inequalities, I'll mention later, something weaker than log sub love actually implies the sub-Gaussian constant, but in the 2-point case, we don't.
So this is already an example when P is
Yes.
small where the
Yep,
asymptotically
yep,
different.
Yeah. So this is all I had to
Oh,
say
okay.
to Svante at the time, and but I'll say.
And then you tensor it.
Right. Yeah. But he wanted an honest to goodness. Yeah, this a complete graph is a similar story. Maybe let me go through a bit more quickly. We showed an extremal type of result, which is actually somehow implicit in a concentration inequality that Bolabash and Leader had shown over all product graphs with uniform measure. What we showed is that over all graphs on n vertices, what the maximum of the sub-Gaussian could be. Turns out, it is this, and it's achieved by a path on n vertices, order n squared. So those are basically all the examples where I know precisely what the constant is. So the 1, 2, and 3 so far we've seen. The rest of them are some estimates and so on. So the next simplest example we thought was a cycle, because again this tensorizes to give you the discrete torus. And there was another motivation, as you see. So the green was the motivation, namely, again there are results from the 80s or 90s of Bolabash and Leader, and then followed up by Oliver Riordan, which settled the isoperimetry problem for the products of paths, also products of cycles. What do I mean by that? What I mean is, so the discrete isoperimetric problem is, or one of the discrete isoperimetric problems says, I give you k, which is an integer parameter from 1 up to the number of vertices, and for each k, can you tell me what is the subset that minimizes the edge boundary or the vertex boundary of your graph? Because for each k, it's kind of an ambitious task.
What is K?
So k is a parameter ranging from 1 up to n, if n is the number of vertices.
It's not related to this case.
Sorry, it's not related here. So let's take L.
For a given graph, what is this L? What is it?
For each L.
For each L, you're looking
On
at
L many points,
Oh,
what is the subset that
okay.
minimizes? So like Harper's result.
mhm.
Harper proved, for the cube, that it's the Hamming balls versus half cubes and so on. You're asking that more generally about other graphs. And Bolabash later results show this for torus and grid, but not for the odd torus. So this is still open for if I start with a cycle of odd length and take the product.
Even for the triangle or something?
Yes, I believe so. Yeah. So they have some conjecture. So what happens is there's some symmetry that breaks down. In the even torus, you have the symmetry. In the odd, you don't. So they have some conjecture that either this sequence of nested sets or their complements are the extremal sets. And they mention a particular ordering of the vertices, reverse lexicographic, or not lexicographic, but some order. And so this was our motivation, or one of the motivations to study this particular case, namely, since the isoperimetric problem is open, can you say at least an estimate by bounding the sub-Gaussian exactly and saying how does the deviation inequality behave? And even the stuff in blue was actually quite tedious. Which is bounding just the second moment. Right? You take a cycle, and what you're saying is over the Lipschitz function, so across an edge you don't want to differ by more than 1. What is the function that maximizes the variance? It's, you can guess what it is. It turns out it's just distance to a point. You start 0 somewhere and then go 1, 1, 2, 2, 3, 3. But somehow it's just like a 2-page calculation that's extremely uninspiring. But that's you can do that and prove what it is for the even and the odd.
No, so You don't know the sub-Gaussian for the triangle because
I do know. I know the sub-Gaussian. I don't know the answer to the isoparometric problem. So I take a triangle and I take the product of that. So I get this torus that started with this.
and then you ask what's
And
the
then I
best.
ask for each L, what is the subset that minimizes the edge boundary?
And
let's
you have
say.
a guess?
Yeah, or not me, but Bolobas, Riordan later have a guess, which I have to describe some slightly complicated ordering, and then they say the sets that the initial segments in yes, or their complements, because so in the even torus case, it turns out you can automatically handle the complement because of some symmetry, but not odd. So I'll mention it's not a question mark. We know up to 1 plus little of 1 that in fact the sub-Gaussian is also equal to spread in the odd torus case. It's not surprising, but it's surprisingly difficult, as it turned out, to show that. So one more example before I continue with a little more with the cycle is another natural example where people studied deviation inequalities using, for example, martingale idea and so on. Moray had some work where he didn't take the transposition distance, he took the Hamming distance, but they're fairly closely related. So again, my space now is the n factorial permutations on n letters, and adjacency is two permutations are adjacent if they differ in a transposition, not necessarily adjacent, random transposition. Okay, anyway. So here we could get, again, this is I think an interesting problem in the sense of knowing precisely what the value of it. We can get, so a bound like this from above, and then just bound, even this I don't know, the variance, that's probably doable, but yeah.
Are there examples where the function that maximizes, say, the second moment is not just the thing that you would expect it to be?
What is the thing that we expected?
You start with a version,
No.
find 0, and then
That this is distance to. Actually, so let me see. I know. So Alon Bapana Spencer showed the following: that there's always some subset on which it's 0, and then it's up to sign distance to that. So you know that that's how it is. Yeah. Yeah.
You at least have some inequalities. I'm sort of back to my example.
Yes.
But are there some inequalities relating these two constants to the time to stationarity, to the time of the random walk to stationarity? They look very close, right?
Consider
Yeah. Not.
that can only be true for constant degree class.
Yeah. Okay. So he's asking the right question now at the right time. Sorry, I mean,
You can pay me later.
okay, so here is again something completely. I show proofs of only completely trivial things, unlike Ryan. So if you take a graph and some random walk on it, or so P is my transition probability matrix, and say it converges to the distribution you have on the graph, pi. So the definition of lambda of P looks something like this, right? So you minimize this Rayleigh quotient, or however way you're familiar with Dirichlet form, which I wrote down explicitly here in the second line, divided by variance. And so of course I get an inequality because I threw in, now I'm minimizing over a smaller set. I threw in the Lipschitz condition. So once I put that in, so I have pxy positive across adjacent neighbors, right, on a graph. So f of x minus f of y is at most 1 because of the Lipschitz condition. Once I say it's at most 1, the rest sums to at most 1. Equal to 1 actually. Sum over all xy, pxy pi x equals 1, so the 1/2 stays here. And now just this is the same as maximizing variance. Okay, so this is just, but unfortunately this can be off quite a bit, like dumbbell graph, or take those where the diameter is small, so this stays small, but then lambda can be pretty bad. However, here's a curiosity. So it turns out, if you, so I mean, it's too much to expect, right? If when going back here, I started with a graph. All I'm using about P is that the support of P is on the edges. But then I could put whatever rates I want. So I'm not taking the natural symmetry. So maybe that's to be expected. But we found an interesting connection to the following question that was studied by Stephen Boyd, Percy Diaconis, and their students at Stanford. Namely, you given a graph, and now and you have a measure that you want to sample from or whatever. It could be uniform, it could be some other probability measure on the vertices of the graph. It's a very reasonable question. The question is, all I care about is not cheating, in the sense use only the locality of the graph, but then use any kind of probabilities you want for P so that it converges to the desired distribution pi. Okay? So you cannot put positive values across a pair that are not adjacent. But if they are adjacent, you could choose to put 0 there. Okay, so they called it the fastest mixing Markov process problem. So they looked at the continuous time version for much of this question, and so I'll say how you could or could not cheat in continuous time. But before that, the question again is, you're given a graph, and then what's the fastest? Fastest in what sense? Say the spectral gap of the chain should be as large as you can make it, right? So fastest in that sense, because the inverse of spectral gap will give you bounds on mixing time and so on. And so it turns out you could relate, you can get a better inequality in terms of the spread constant to this lambda star, to the optimal one that you could. And you lose, and this is actually quite easy. This bound, it's much darker here. The log V is actually is quite easy once I tell you the connection. So a natural thing you might,
The example that shows it's almost tight are so how small are the quantities there? I mean, or I guess so.
we need the third organizer, Asaf Nauer. Yeah, it's been a few years, unfortunately, since we did it. And you saw question. This is one of those papers he promises to write in. But there's a class, I don't remember it off the top of my head, but it was a robust example using the doubling metric space idea. And so you can, if there's a parameter lambda in the doubling metric, I didn't want to use because of spectral gap. Then in terms of that, you can get log lambda, log lambda, or something like that. So he had a construction. But again, expanders, he believes, could actually give maybe a better tightness. He believes maybe, but the log is easy. The log is easy, and maybe that will inspire you to think of why I'm claiming the second result, because the second one I don't remember so well. But the log is simply because, so you take the variance, so a computational question, by the way, just the second moment, the spread constant, maximizing the variance over Lipschitz function. I don't know how difficult it is, but one of the things you could do is take the semi-definite relaxation. Okay, so now replace the Lipschitz function by, for each vertex you have a vector in Rn, yeah, and so it's the second one actually. So it should look like something like this. Take the L2 norm squared and replace the Lipschitz condition by, again, that the norm be at most 1. It turns out this is something that they studied, the guys doing FMMP, fastest mixing Markov process. And so if you go to the blue formulation, which is the same, I'm maximizing second moment in one dimension. Okay, as we write, variance can be written in two ways, right? You write as the second moment minus square of first moment. Here the first moment is 0, so that's, or another way is as this. So in one dimension, what I'm saying is that this is exactly the spread constant. But now you can take the n-dimensional version, where I've replaced f of x, f of y by xi, xj, which are vectors in Rn, and I replaced the absolute value by, right? This again, for the CS audience, this is the standard thing. What they showed is that lambda star, namely the spectral gap of the fastest mixing Markov process, is inverse of the optimal value from this program. And this, as you know better than I do, can be solved efficiently in polynomial time. And now you do the Johnson-Linden-Strauss lemma that says you can actually do dimension reduction to log n from n. And so it's an easy proof to show you lose at most log n in doing that. Okay, so that's the gist of the first part. And yeah, let me not say anything about the second part since I don't remember now. So here is the answer to the very first question Avi asked. That shows that the two are, say, typically different, but so it's not so hard to prove the first lemma. Okay, there's a sort of somewhat standard argument I found in the paper by Alon Millman. One can use in proving a general lower bound on the sub-Gaussian that says at least square of the diameter divided by log n if you have uniform probability measure on an n vertex graph. Okay, pi is general probability measure. Pi star is the minimum, okay, minimum entry. And so once you have that, then it's easy because now you're trying, so you know that the sub-Gaussian is at least something. So you take diameter that's faster than log n, diameter that's log n or so that d square gives you log square n and the denominator gives you log n. But then you want to control the spread constant. The spread constant we saw is at most 1 over spectral gap. So if you take a bounded degree expander, right, by definition the expansion over the spectral gap is bounded, and so is the spread constant, but sigma of g could be like log n. Okay. Okay, so back to the yes.
Sigma of g related to the best embedding the graph would have into L1 or L2.
I don't know. I have no idea. It's, yeah, I don't know anything in that direction. I mean, there is a reformulation of sigma of g. I'll show you, and that's the transportation inequality. So it's an inequality relating the Wasserstein distance between two measures and the relative entropy. And that's a result of Babkov and Goetze, not ours. And, but the only thing I know is through the spread constant. I think for planar, Asaf also mentioned to me that for planar graphs that log n can be replaced by a constant. So for planar graphs, the spread constant you can estimate up to a constant, again from embedding literature, doing some standard stuff. But for sub-Gaussian, I don't know. Yeah. Okay, back to the cycle. So what did Marcus Sammer, a student of mine, and I do? Again, there's some double dates because I learned a lesson. Don't graduate the student until the paper is written and submitted. So the question mark I had in one of the earlier slides, as I said, the sub-Gaussian of the odd cycle you can show is up to little of 1, is the same as the spread constant. And so I'll say, so the result is not as interesting as maybe the approach we took, which I thought there would be a slick proof by cheating, by looking at an alternative formulation of the sub-Gaussian. So for that, let me introduce again at the sure possibility of offending several experts in the audience. So I want to get to an inequality of Bobkov and Goetze that relates a relative entropy of distribution mu with respect to pi and another distance. This one is actually, unlike relative entropy, a true distance, true metric, so-called Wasserstein L1 metric. But so for that reason, let me define formally what I mean by W1. So in this context, actually the inf is a minimization. So you have you can define this as Kantorovich did more generally for measurable metric spaces. But for us, in our context, so you have a graph, and then there's some underlying distance d, and what you're doing is you're minimizing overall couplings. Okay, so gamma is a joint distribution with marginal mu and mu. So W1 of mu nu is simply the minimum cost to move mass from mu to nu. Okay, so if in the joint distribution gamma, if you move gamma xy amount from x to y, then the cost you pay is d times xy times gamma, right? So again, you might have seen it as earth mover distance, etc. So this hopefully is the so-called Monge problem is familiar to you. And then sometimes the dual of that. So for us in the finite dimension, it's just an LP. You're minimizing, what you're given is the d. So you're minimizing a linear objective function. The variables are gammas. The constraints are linear because gamma is a coupling. That's a linear constraint, that sum of gamma xy over x is mu and over y is nu and so on. The dual version, sometimes referred to as the Kantorovich problem, is you're maximizing over, right? So here is the connection over the Lipschitz function. Turns out, this is again, I'm using something specific that while one could study this for any cost function in place of dxy, some cxy, I'm using that. The cost function is a distance. Okay, this is a metric. Otherwise, this looks different. So, using the fact that d is a metric, it turns out it's equal to maximizing this quantity over Lipschitz functions. Okay, so again, the connection to d is hidden here. The top one has a d. Where is the d? D is hidden in the Lipschitz. Yes? So, I meant to write a bullet down here saying, in case you haven't seen this before, if d is 0, 1 valued, okay, so dxy is 0 or 1, then this version, for me this is easier to see, this version tells you that in fact this is the total variation distance between mu and mu, okay, in the special case of, but otherwise it's the W1. So why W1? Again, in the continuous cases, much more has been done working with WP, in particular W2, where W2 square is going to be the same right hand side except d will be d square. Okay, so W2 would be square root of the summation d square gamma and so on. And okay, so and a paper that sparked quite a bit of work since by Bobkov and Goetze, which had a few results. So one of the results that we work with is the following. It shows that the sub-Gaussian inequality that I showed you is equivalent to this so-called W1 transportation inequality. W1 transportation, or sometimes called L1 Talleyrand inequality, because Talleyrand used this with W2, such an inequality. So again, their assertion is that they did it in a more general context, which discretizes simply, is that the same constant c is in the two.
So there is no slackness of the two.
No slack, yes. So it's a completely, yes. So I could, this is what, so when I saw this, I thought, okay, now I can solve the odd cycle problem. This maybe somehow magically this is, because each of these quantities are much well understood and so on. So one of the general open questions is there, are there things that we could do more nicely with this. So we proved some general, general type of propositions towards solving the odd cycle problem, but still we have a 10-page proof or something. So it's kind
Can
of.
you repeat what is the odd cycle problem?
Oh, just say the sub-Gaussian for the odd cycle. Yeah. I mean, a harder problem is solving the isoperimetric problem. When you take the product of odd cycles, how do the extremal sets minimizing, say, the edge boundary behave? Right. That's a harder problem. Yeah. And as I said, this led to very nice work by Felix Otto and Cedric Villani, and then Babkov Gentil Perdue, who's here, and several other people. I don't have time to give the general context of which directions people took this in and so on. So let's see. Now I have to optimize.
Better, more favorable.
Okay. I see. Take the min or max of the two. So I'll just mention briefly the steps involved in proving using the transportation formulation. Okay, so again the sub-Gaussian inequality, and then it's a completely equivalent constant using different types of quantity. But one of the curious things we showed, and this again comes up in log Sobolev type inequalities, is that if the sub-Gaussian, let's see, maybe the contrapositive is better to say for step one. So if there is no minimizer or whatever, if there is no if nu is not achieved in the transportation formulation, then you can show that the sub-Gaussian and spread constants are the same. This is similar to people familiar with log Sobolev inequality. If you know there is no log Sobolev inequality, there is no function that achieves it, then it's known that the constant is equal to the spectral gap. And that's also true for some of the modified logarithmic Sobolev inequalities. So this is useful, for example, in trying to show that for the even cycle that the two are the same. Okay, so using the contrapositive. Item 2 is like the result of Alon Bopana Spencer about the spread constant I mentioned. Okay, something about distance to a set, and so in this case, so there's a Lipschitz function in the transportation formulation in the W1 dual Kantorovich formulation of W1, right? So for a minimizer or maximizer, that function is distance to up to sign distance to some set, and again this for the cycle it's in fact a singleton, so it's even less of a search in terms of finding. Okay, the third one, let me skip that, it's a bit technical, but it basically relates. So in the two formulations given by Babkov-Goetze, you have f and t in one, and then you have the transportation formulation. It says something about if you know f and t, the optimal ones there, it gives you information about nu in the and the Lipschitz function that comes up in the dual formulation of W, because it's some technical results, but just to give you a flavor of how somehow non-trivial it is to estimate this for some fairly innocent looking graph like a cycle. Okay, so quickly, connections to log Sobolev type stuff I promised. So this is it has a couple of names. So we called it in a paper with Sergei Babkov modified log Sobolev, where I have not EFF, not the usual Dirichlet form, but I have F log F. But and then we realized actually several other people did it, and some before us independently. Namely, what's the natural way to arrive at this is by saying you have some Markov chain, say continuous time, you take a distribution at time t, and a natural way to measure how close you are to stationarity is by relative entropy as opposed to total variation or some other norm. And the derivative of that turns out to be related to this modified Dirichlet form. Namely, Dirichlet form is ft log ft rather than ft, which you get for Poincaré. So if you take variance, then you get. So that's a natural way to introduce this modified logarithmic sobolev inequality, because now you want to say, can I relate ft log ft to entropy of ft, so that I can solve a simple differential equation. So the gist is that this rho naught controls the decay to convert to equilibrium, converges to equilibrium in the entropy sense, in the relative entropy sense. Let me skip some of these. So to do a systematic study, we looked at various of these inequalities. Some of these introduced by Ledoux, above Prof. Ledoux, the modifications of the logarithmic Sobolev inequality. So the classical log Sobolev is at the top, and then these are all some variations, and we showed that they progressively approach the spectral gap. Right? So the reason I'm subjecting you to this is to say, so this is sort of my understanding at this point. In terms of sub-Gaussian, is it related to mixing time or any of these? So we already saw that this could be quite a bit different, right? Unless you study the fastest mixing. So what Poincaré implies this could be quite a bit. These are equivalent by Babcock-Goetze, and there's a proof by Otto and Villani that shows log Sobolev inequality implies the stronger W2 transportation inequality. So we tried to mimic that, but what was more natural, turns out in the discrete case, is starting with a weaker, such as rho 0, and ending up with a weaker inequality. So what we show is rho naught actually implies this inequality. What's also easy to do, and it's using an argument, sometimes people say Herbst argument, I've seen in a paper of Ledoux. You can also go from this slightly weaker rho 1 inequality to derive the sub-Gaussian. So this is just to say the usual log Sobolev type inequalities are already too strong, but they give you bounds on this.
You're getting something different by the double arrows and the single arrows?
No. Actually, this I had help from.
Two arrows are diagonal. It's hard to see.
I had help from this amazing admin help we have. That so it was her drawing I didn't tinker with. Even by this clock, I'm in trouble. So let's see what I want to say. Yeah, I said this already using. Let me. So you might be wondering where I'm going next. So I'll simply say what seems more exciting now is this type of stuff. And since I mentioned briefly displacement, convexity, and things like that in my abstract, I wanted to say this is just a small beginning, but looks interesting. So you'll see in Sturm's talk more along these lines, that in continuous spaces they know quite a bit about convexity properties of entropy, say entropy of Dijkpraal will talk about entropy of distribution of a Markov kernel, and or in the case of spin systems, but what's a challenge is how to interpolate between two measures. So the game is you have two measures, mu0 and mu1, and what we managed to do is on a 2-point space. Even here it's interesting, non-trivial, and it's not obvious. So you have two measures. What you're trying to find is an interpolating path on the measure space. So mu alpha, okay, for me is a measure that at alpha equals 0 is the first probability measure, at alpha equals 1 is the second. It's too arbitrary. And I'm trying to relate, once I tell you what mu alpha is, I'm trying to relate the relative entropy of that in terms of, so it's a sort of a convex type of inequality, but it's a bit stronger because I have in fact a negative term here. Okay, so here it's total variation because in the 2 points, the distance 0, 1, I told you Wasserstein reduces to total variation. So, but in continuous spaces, the kind of inequalities they have are of this type, where this term depends on the so-called Ricci curvature and so on, or a bound on the Ricci curvature. So, one general question in discrete spaces is, can we find such analog? Can we try to understand the notion of discrete Ricci and so on? And there are some attempts, there are some descriptions. So, what is mu alpha? And then I'll stop. So, mu alpha is the law of the following random variable. Okay, so take two random variables x and y. X distributed as mu 0, okay, using mu 0 is the law. Y according to mu 1. And now you take the mixture x plus the sine of y minus x times Bernoulli. Okay, random variable distributed at Bernoulli with alpha. Okay, so for alpha equals 0, this is going to be x, alpha equals 1, it's going to be x plus y minus x, y. Okay, but for alpha, anything in between, it is what it is. So T alpha is the interpolation, and then mu alpha is the law of that. So if little x is 0, take sine to be 0. And it seems interesting because it gives a way to derive a modified or the entropy inequality, the modified logarithmic suburban inequality with a particular constant. Seems a little bit weaker than if you tried to work directly, because it's 2 points. You can be brave and try to work directly. You get something maybe slightly better, but the point is, are there ways, this is my general question, you can derive some of these inequalities in an easier or softer way than what I've indicated. So let me stop there. Yeah.
Questions?
Yeah.
The mu alpha that you find here, are
Yes.
these the W2 Wasserstein geodesics, or
So one question is, we don't know the appropriate W2 in discrete spaces. And in fact, we know the W2 inequality, if I translate it by just squaring the distance, it doesn't hold. So we know we know what not to do. So here at the top chart, as I said, Otto Villani show something like the right hand side. Rho is the log subular inequality. It implies a W2, a Talleyrand inequality. Square of W2 is that. We don't know, what's the right discrete analog for W2. Yeah. Yes?
I not really understand. I mean, you have the optimal constant for the modified log subular in 2 points?
No. Yeah. In the paper with Bobkov, we had said, well, it's at least whatever I wrote here. Well, we don't know. Yeah. Yeah. Good question. So one attitude is, okay, there's 2 points. You should know this before you go anywhere. I guess the second defeatist attitude is, can you give me something that works in more general spaces, more robust proof, even if it doesn't give me the optimal. I'm happy with either.
Other questions? Okay, thanks.